Finally, let's talk about how to put together all of the different reactions that we've been talking about in previous sections. There's two ways to look at problems like this. One is by looking at synthesis. How do we use these things to build new molecules? The other is mechanism. How do we explain the manner by which they happen? One example of how these reactions can be extremely versatile when used in combination is this reaction here. So in this reaction, I'm going to take a cyclic beta diketone and treat it with sodium hydroxide and an alpha beta unsaturated ketone in the presence of heat. This reaction will give me a new highly functionalized six-membered ring in a single synthetic step. This is known as the Robinson annulation. As a way of checking out your skills from all the previous reactions, explain how this reaction works and try to do so without proposing a full arrow-pushing mechanism. Work your way through this, then restart the video and we'll check your work. Looking at this reaction, we can see that if we start this with our beta diketone, sodium hydroxide, and the alpha beta unsaturated ketone, that this looks a lot like a conjugate or Michael addition. We would deprotonate the highly acidic beta position and add that doubly stabilized enolate to the beta position of our unsaturated group to create this ketone. If we continue under these conditions, sodium hydroxide and heat, this now looks a lot like an intramolecular aldol condensation, which would explain why we get a new six-membered ring and a double bond. If we're looking at this from a purely synthetic perspective, we want to look for patterns in difunctional compounds that indicate which reaction happened. For example, if we take either the aldol or the Claisen condensations, we can see that we get a 1,3 difunctional compound at the end of this process. We can make a 1,3 hydroxyaldehyde, a 1,3 unsaturated carbonyl compound, or a 1,3 keto ester. These are distinctive fingerprints that indicate that these processes have taken place at some point during a synthesis. On the other hand, if we look either at the Stork-enamine synthesis or the malonic acetoacetic reaction with a conjugated substance, we get a 1,5 difunctional compound, here a 1,5 diketone. So now for some practice, I'm going to walk through how we would apply this reasoning to two fairly straightforward examples. Starting with 1-propanol as my only source of carbon atoms, I want to make both of these different diols. The way I would start is I would look for patterns. So can I take my two targets for this synthesis and find either a 1,3 pattern, indicating an aldol or Claisen reaction, or a 1,5 pattern, indicating either an enamine or a Michael addition? I can find the 1,3 pattern in the leftmost diol and the 1,5 pattern in the rightmost diol. Notice that also by doing this, I've also found new carbon-carbon bonds between my two 3-carbon starting materials. For the next step, I want to deal with functional group transformations. Now my target molecules were both alcohols, which means that I have to figure out where the carbonyl groups used to be. Assuming that I did an aldol reaction, I can turn one of my alcohols back into a carbonyl group and get this beta keto alcohol. If I assumed a Claisen condensation, I would have this beta keto ester. Now looking at these two things, the Claisen condensation would produce an ester, which would mean I'd have to deal with more carbons. Since this is a little more complicated, I'm just going to rule that one out. For the other alcohol, the one with the 1,5 pattern, I'm going to assume a Stork-enamine synthesis, which would mean that both of those used to be carbonyl groups, in this case aldehydes. The malonic or acetoacetic ester syntheses don't make sense in this case, since both of those involve a minimum of 4 carbons and would have to do extra synthetic work. Once we've done this, we can work our way backwards to find appropriate nucleophiles and electrophiles for each transformation. For instance, if I take my aldol product here, I can split it at the alpha carbon and generate an electrophile and a nucleophile. For the 1,5 pattern, I can again split it at the alpha carbon and I can generate a nucleophile and an electrophile. Now that my carbon-carbon bonds are taken care of, what I can do is I can treat this like a synthetic problem from earlier in the semester or in 2131. When we don't have to build new carbon skeletons, we mostly just have to deal with functional group transformations. So based on the groundwork that we've laid here, go ahead and try to work your way through the rest of this synthesis, and then I'll work through it and we can compare our two methods. So our restriction here was that all of our carbons need to come from this 3-carbon piece. So the obvious first step is to oxidize this with PCC to the aldehyde, and that will produce our nucleophile and our electrophile for the Aldol addition for our first target. Once we do the Aldol addition, we can reduce the other ketone with sodium borohydride to give this diol our final product. The other synthesis is a little more complicated. We would need to make an enamine out of the aldehyde for the Stork-enamine synthesis, and we would need to also make the alpha-beta unsaturated compound by using the material back from the alpha halogenation section. So here we would treat the aldehyde with diethylamine in the presence of an acid catalyst to make the enamine, and the aldehyde can be treated with bromine under acidic conditions followed by pyridine to generate the unsaturated compound. Now we have our starting materials for the Stork-enamine synthesis, so we would combine these together in a first step, followed by H3O+ as a workup to hydrolyze our products back to carbonyl groups. This will give us this dialdehyde. Since our final product for this target is also a diol, we would need to reduce those, and sodium borohydride would be an acceptable reducing agent for that as well. It's very important at this point to practice synthesis. So to practice, be sure that you've worked through every single in-chapter problem in Chapter 21, Section 7. And when you do so, you want to work on these without assistance. No notes, no book, no internet, just you and your brain. If you get stuck, use these resources in this order. The first source that you want to have is your notes from when you work through the other chapters in the first place. The second thing you can do is go back to the textbook looking for reactions that you need. The third and final source is if you really get stuck, ask someone else for help, including me. When you work through these problems, be sure to use retrosynthetic analysis. If you don't have a good plan when you start, these problems will be basically impossible to solve. And finally, when you're done, check your work. Work your way back through each reaction going forwards, being careful to look for side reactions, proton transfers, and anything else that could interfere with your process. That finishes out Chapter 21. In the next set of videos, we'll move into Chapter 22, which will discuss the chemistry of amines.